Okay, Professor Khalik, will you talk about the tutorial, or it's something like a lecture?
It's kind of a lecture,
Okay.
but I try to make it interactive.
Okay, that's great. Okay.
I'll show you something.
It's okay. Okay, hello everyone. So let's welcome another session. And now we have Professor Thomas Kale with us, and he will talk about how binomial primary decomposition will work. It's okay.
Okay. So
Okay,
welcome back, everybody. So in my last slot here, so unfortunately I didn't really plan this so well ahead with all the exercises, but I hope I can make this a slightly more interactive session and post some quiz questions as we go. And so I want to show you a bit under the hood what kind of computations go into this binomial primary decomposition. So let me show you what I think is the most crucial lemma about primary decomposition. So let's start. I hope this is relatively synchronous. So if you have an ideal I in the polynomial ring, this need not be a binomial ideal as of yet. So now I'm talking about general ideal I, and then you know it has a primary decomposition. And to find primary decomposition, we always first try so-called splittings. First try splitting. Okay, what is splitting? So the name comes from the following. If you think about the geometry, V of I, the variety. So I think of the variety like this. Maybe there's a plane. Okay, something happened. You're not seeing this anymore. I'm not seeing it anymore.
Share your screen.
Yeah, I think this was my computer's problem. Okay, we're back. Sorry about that. Okay, so I was just drawing this sheet of the variety, and now if we do primary decomposition, then we expect that this is somehow a reducible set. So maybe there's another component that's a curve, and then there's some isolated points somewhere or so. So it's a reducible algebraic set, and we want to find the components. And so the idea is, geometric idea is to split using an f, which is a polynomial, that is 0 on one of the components and not on the others. Yeah, so say you find some polynomial that vanishes on this plane, and so it's a hypersurface, vanishes on this plane, and it doesn't vanish on this line and these points that are not on the plane. And if you do that, you can, if you find such a thing, you can do an algebraic procedure that. So what does it do on the algebra side? So let me first remind you of my favorite definition of primary ideal. So I say an ideal I is primary if in the quotient every element is a non-zero divisor or nilpotent. So non-zero divisor means multiplying by that element is an injective map, or you can cancel. If you see that thing, you can cancel it. And nilpotent means a power is 0. Yeah, so it has at the moment nothing to do with the nil from yesterday. Here nilpotent means just a power is 0. So now here's a very naive primary decomposition algorithm. Well, it doesn't work, but in principle, it's a nice idea. So either I is already primary, then the algorithm is very easy. You output I, or you find this F, or find F that F in the quotient that is not nilpotent and not zero divisor. Find F zero divisor on the quotient that is not nilpotent. If you go back to the algebra and geometry dictionary, you can convince yourself that this is such a splitting F. It's something that vanishes on one of the components, but not on the entire variety. So then you use this lemma that my exercise will be, my ad hoc exercise is to think about the proof of this lemma. So what does this mean? F is a zero divisor means that I colon F is strictly bigger than I. And I is not nilpotent means that if I put it just means no power is contained. Okay. F to the S not in I for any S. Okay. And now here comes a very useful lemma. If you take S is a natural number such that I colon F to the S equals I colon F to the S plus 1. So we have found this F, and we do I colon F squared, I colon F cubed, and all of these might become larger and larger, but because we are in a Noetherian ring, the chain will stabilize. So that means there is one of these S's, there's an integer S such that it doesn't grow anymore. And I take this S, the minimal, let's say the minimal one. Yeah, may take minimal. Okay, and then my lemma just says that I is equal to I colon F to the S intersected with I plus F to the S, or I write comma here. So the second one, that's the ideal generated by I and this one polynomial F to the S together. Okay, so both of them are strictly larger. Both are strictly larger. Both larger by the choice of this F. You can also learn something about the associated primes. So that geometric idea that we had above here with the component, so here you remove the component that corresponds to F equal to 0, taking account of multiplicity in case it should be there. And here you restrict to that, yeah, the hypersurface that generated F. Also taking care of multiplicity. Okay, shall we take 5 minutes to think about this lemma? It has not many ingredients. So the crucial ingredients are the choice of this S, and of course, check this containment. You check 2 inclusions. One of the inclusions is really easy. The other one is the thing that's to prove. Okay, that's my part where you can do something.
definition of this common FS.
Oh yeah, so in case you, I will not say something, but I will remind people of the definitions of the two ideas by writing.
Okay. So they, why?
Okay. Any comments? Anybody here or there wants to tell me what to write? So let's first sort out which of the inclusions is really easy. We have I contained in the right-hand side and the right-hand side contained in I. In Germany, we always do it like this. We write our funny quotes with lower quotes and upper quotes. And then colon, and we write the two proofs behind this.
I think that the lower one is easier,
Which one is easy? The lower one?
the lower inclusion.
You mean this? Okay, I. Okay, so anybody please, I will not please tell me something for one of the two cases.
So,
I'm
Professor
done
Keller.
with one side.
Yes.
Sorry, can you say again?
I'm done with one side.
Okay, which one?
First one.
Okay, the first one. Why is it true?
Because I contain the second one ideal I and fs is generated by both ideal both like I and fs, so I contained in both in this ideal. Then because I is an ideal, so for every polynomial of I, the product of element of I and fs belongs to ideal, so that's why it contains in this ideal as well.
Yes. Okay, so you check for both individually. This one is really obvious. And this one you check with this formula by putting an element of I here. You get an element of I times something, and of course it's in the ideal. Yes, this is what you just I mean, and I will throw for it. Just try check mark. Okay, and this one is a little trick. So last chance, anybody wants to say the trick? Okay, so I will lead us through the argument. So we want to show that something that's in both is in this side. So one way to do it is to start with a general element here, and I call it G, and I assume it's in this ideal, and I'm going to say it's going to be of the form I plus some coefficient, what we call it A times F to the S. Yes, so an element there is a general, is some polynomial combination of elements of I and this F to the S. And of course, if it's if this A is 0, then the task is trivial. So I will assume it's like this. So I is in I, and A is arbitrary. This form I can assume. Now I also know that it's in here. So if I multiply it with F to the S times G, that's in I. So F to the S times I plus A times, now I can just put those together, F to the 2S is in I. That I get from this second containment, yes? My element G is in both. So it means if I multiply it with F to the S, I land in I. Now, what kind of simplifications can we apply here? We see that this is, of course, in I, this first summand, because it's something in I multiplied by F to the S. So we conclude that A, F to the 2S is in I. I need a new page here. So it follows that A, F to the 2S is in I. And here comes now the saturation property. Yes, if I multiply A by F to the 2S, I land in I. But this means I can already multiply it by F to the S and land in I. So if I want to spell this out more, that means A is in I colon F to the 2S, but the chain has already stabilized. So F to the 2S is the same as I colon F to the S, because after F to the S, nothing happens anymore. So that means A times F to the S is an I. Oh, but that means that G actually composed of two summands that were both an I, so G is an I. Okay, so why did we do this? We did this because this lemma can help us with primary decomposition. Both of these are larger ideals, and my thinking about them is they are closer to being primary, because that F before modulo I, it was not a zero divisor, it was a zero divisor and not nilpotent. So now when you do this operation, now F is regular. You made it so whenever G times f to the s is in I, which means it's 0 in the quotient, you just put g also in that new ideal. So now f is regular. Now from something times f equals 0, it follows that the something was 0. Because we put all those g's in this new ideal. So modulo this ideal, f is now a non-zero divisor. I call it regular. Sometimes people also call it regular. Yeah? So modulo that ideal, f, we have made f a non-zero divisor now. Modulo that ideal, we have made f nilpotent because now a power of s is in that ideal. So modulo these two ideals, this f that we use to show that the original ideal was not primary is out of the question. It's solved now. And now you can, in principle at least, continue with these ideals. So after the split, this is the split, this writing this intersection. After split, continue with both ideals. So they are either primary or split again. Okay, so you get kind of a tree structure. Yeah, you start with I and you split it in I colon f to the s and I comma f to the s, and these might be primary or not. So maybe one is primary, the other one splits again, and maybe this one is primary and this one splits again. So you build one of these trees, and the intersection over all the leaves of the tree, because this one, each ideal here is the intersection of its two children. So the ideals along these chains here, they're always included in each other and they always get larger. And now we're in a Noetherian ring, so the procedure has to stop. So the tree must be finite, tree finite. Because the polynomial ring is Noetherian and there are no infinite ascending chains. Okay, now here's the next question. If I now tell you, yes, please.
So when we split, we will get these both ideals. So for the further splitting, we will use the same idea. Like for one ideal, we will split the ideals in the same type of ideals.
Yes, you would find a G. So for both of these, you individually do the argument. Either it's primary. If it's not primary, you find F2 or G.
Okay.
And then you split this ideal as itself colon G to the S prime, and yeah. So you do it inductively. You start again with step 1 from this ideal.
Okay.
And you have to. Okay, so now my question, if I give you the task, okay, now go to Macaulay 2 and implement this primary decomposition. It's a primary decomposition algorithm. What's the problem? Could this work? I mean, I already hinted that the answer is no, because yesterday I said primary decomposition is complicated.
Can we also split the right one?
Yeah, in my example, I assume that this is maybe primary, yes? So yes,
If it is not.
you keep splitting until it's primary.
Okay.
And it must be primary because it becomes larger and larger. And if it doesn't become primary, you would construct an infinite ascending chain, which is impossible because it's Noetherian. It's the beauty of this Noetherian induction. It's called Noetherian induction, this process. Okay, think about step 1. How would you implement step 1? Step 1 was either I is primary. Okay, you need to test if I is primary. And that's already the big complication. So how do you test if I is primary, or if not, find this witness, the splitting element that is not primary? And this is in fact, this is the major complication. Yes. So here on the paper, I can just say, okay, you do this, but in reality, you have to. All the problem is in this. Yes, or in testing if something is primary or finding the splitting element is complicated. So you can do it like this, but for binomial ideals, now we get to binomial ideals. Anything more I want to say about this? Yeah, now comes the big green but. For binomial ideals, it makes a lot of sense to use only variables as f. Okay, very simple, only variables. So this it makes sense relies on theory from the paper Binomial Ideals by Eisenbart and Sturmfeld. So you can do this without a computer. So let's do the example from yesterday. The monoid with two ones. Remember the monoid with two ones? 1 and 1 prime. So the ideal for this monoid had two generators. So this was approximately the picture. And the ideal was x squared minus xy and xy minus y squared. Okay, so now my exercise is find a variable that is a zero divisor and not nilpotent. Then split. What do you find? Yeah, so you get a decomposition of I. What is it?
The zero divisor of x plus y. What are the zero divisors?
You can speak. You can speak.
Maybe the x.
Okay, let's do it with x. Because of the symmetry, x and y both work. So that's good. So they have you computed I colon x? I think it can be computed in our minds. Because look, one of the generators is divisible. So this colon, it's not an accident that it looks like division. It's like if you can find something in I that's divisible by x, you can now divide by x exactly one time. So this generator is divisible by x. Okay? You agree? Everybody agrees? So this certainly contains the polynomial x minus y, which is what I get when I divide the first generator by x. Okay, but now if x minus y is there, this generator here is also divisible by x minus y. So I can factor those for you. So this is x times x minus y. This is y times x minus y. This is how the generators factor. So if I put in x minus y additionally, both of these generators become redundant. Yeah, so I don't need to write them anymore. In fact, I colon x is equal to x minus y. And we know that this is a prime ideal because it's generated by one linear polynomial, so it doesn't factor, so you can check by in your mind. I mean, it's obvious that it's prime ideal. Yes, the quotient modulo that is the polynomial ring in one variable, so that's a domain, so this is a prime ideal. The linear ideal also. Ideal generated by independent linear forms is a prime ideal. Okay, so now we need to. So we also, because this is a prime ideal, we also know that I colon x squared equals I colon x. Yeah, so we can use s equal to 1. So let's compute I plus x. What are the generators of I plus x? Can somebody tell me a minimal generating set? Of course, I can write x and then the two generators here, but I could also simplify them a little more. I already write the x.
X comma x minus.
X minus y will not be in there, I think, because yes, x minus y will not be in there. You can just simplify these generators, yes? So this, if x is in there, then x squared is in there, xy is in there, the difference is in there. So this generator we can just leave out. What about the second generator? We need it, but this term, the first term can go because it's divisible by x. Yeah, the first term is this generator times y. So we can just write the second term here, and the minus, of course, we can also leave. So it looks like this. Is this idea prime? No, it's not prime, but it's primary. Yeah, its radical is the prime idea generated by x and y. So this is primary. Oops, sorry. So this is prime. This is primary. And so we have the decomposition of I as x minus y intersected with x comma y prime. Is a primary decomposition. Okay, so this we got lucky. So a couple of remarks. First of all, if we do exactly the same with y instead of x. Okay, if you do it with y, you get that I equals x minus y intersected x squared comma y is also true, is a primary decomposition. So this is a general phenomenon. This is called an embedded component. Embedded component, and those need not be unique. I mean that they're not unique. Not unique. They're called embedded components because their variety is also geometrically something interesting is going on. So this is a line. If you look at the variety, this is the variety of I, if I want to draw it in a coordinate axis system, then this component here gives a green line. It just says x equal to y. X minus y equal to 0. This is the variety of x minus y. And what's the variety of this? This says x squared is equal to 0 and y is equal to 0. That's an embedded point. So the variety of that thing is the origin. So it's contained in the green variety. On the level of varieties, you don't see it, but algebraically it's there because there's a square here. It stands out by the square. If it was x comma y, the intersection would be redundant. We could leave out that part, the larger one, but here it's irredundant intersection. Remember, yesterday I decomposed this ideal into 3 components. Why did I do this? Because here we're making a choice. We're choosing, I either want to use x or I want to use y, and I get 2 different choices. So I was, with the mesoprimary decomposition, aiming at a canonical decomposition that does not make any choices and preserves, if you want to say it like this, the symmetry of the situation. And the only way to resolve this is to include both of these components. Both of these components are combinatorially justified. So in the mesoprimary decomposition, we would include both of them. But that's a matter of definitions, a matter of what you want. Yes, I mean I think the mathematics is clear. So if these 2 decompositions are irredundant. Okay, so now let me just tell you a binomial ideal where each variable is non-zero divisor. So modulo which each variable is non-zero divisor or nilpotent is called cellular. That's the term from the Eisenbach-Stolpitz paper. And this corresponds to, this is like pretty exactly the primary decomposition of congruences. So doing this is primary decomposition of congruences. The one that I claimed was wrong yesterday, that you shouldn't do. But my package in Macaulay 2 does it. It's like the first step in any decomposition is to compute the cellular decomposition, because the reality forces you to make these things. Okay, so that's the first step in the decomposition. And then let's work a little more with the second example that we had. I'm gonna bring it back in by picture to see the second part of a decomposition of a binomial ideal. So remember this example. I will write the ideal again. Oops, why can I write? Okay, now let's say I equals, I go from the top. So there's y cubed, which is the golden area. So then there's y at the y squared level. I see x minus 1. I can do that. I derive that from at the y squared level. I see y squared is connected to x times y squared. So I write it like this. At the next level, at the y level, it's 2 steps. So I get y times x squared minus 1. And at the bottom level, I don't get anything. Yeah, so there are no binomials in these x direction in the bottom level, so I don't have any generator. So this is the congruence, and this is the binomial ideal. Now this is cellular. This is cellular because so x is non-zero divisor. and y is nilpotent. Okay, but it's not primary. Not primary, not mesoprimary. So here are 2 reasons. I mean, you see all these products, yes? So e.g. X squared minus 1 factors into x plus 1 times x minus 1. That's one arithmetic reason, I would call it. Needs to be equal sign here. X squared plus 1, x squared minus 1 here. That's not a good explanation. Wait. That's actually not a good argument why it's not primary. Let's find out. Let's take 1 minute. I need to solve the exercise myself to see the easiest reason why it's not primary. We need to find an element f that's not regular and not nilpotent. Okay, I can see 2 associated primes at least, but what are the f's? E.g. F equals x minus 1 should do it. Yes. F equals x minus 1. If I do colon x minus 1, all sorts of stuff happens. So if I do colon x minus 1, the y squared goes in. And also this polynomial also factors. I get y times x plus 1. So I will leave these computations now because it's not what I want to focus on. So now the lemma says, if I go modulo, so imagine we have this non-zero divisor direction. So this is now, imagine this is an invertible direction. So we have made this, we have localized so that these become invertible. So in horizontal direction, everything is equivalent. So modulo the invertible directions or the regular directions. There is only a finite coset of elements. And in this case, if you go modulo the x direction, only the y direction is left. So I have my finite coset of these 4 elements. These are the 4 elements, and we search for witnesses. Search for witnesses there. Okay, so what are the elementary operations that we can do to these ideals? So the elementary operation is we can do what we did on Monday, extract the lattice for bottom layer. So what I can do is I can take this bottom layer and compute the lattice that corresponds to the congruence there. So in this case, it's the empty lattice. There are no binomials in here. And I would do this by taking my I plus y and then lattice of that. Yeah, and oops. I switched app, sorry. Lattice of that. And in this case, it's empty lattice, 0 lattice. Okay, now I want to find this behavior. So what I'm going to do is I'm going to do colon y. I'm going to go colon the nilpotent direction, which moves the whole picture 1 down. So do colon y, so lattice of I colon y. Again, plus y to remove all the other stuff. And then we get this lattice, which is 2z. 2z because everybody is connected. So if I look at the class of this, it's like every other point is in there. Yeah, 2, 4, and so on. And note that this colon variables really does something very pictorial. So colon y moves everything down one layer. Why does it do that? You can see in these generators, yes? Y squared times x minus 1. If I do colon y, it becomes y times x minus 1. So this x minus 1 part, the blue part, is now at level y. And this y times x squared minus 1 becomes just x squared minus 1. So that behavior is now at level 0. So I find this lattice 2z. And then I do it once more. And I find the lattice z. So in a very early draft, long before all this mesoprimary work was done, I called these associated lattices because they behave like associated prime. Associated lattices. Like associated primes. So and now from those you make the components. Make components. By adding the binomials that correspond to these lattices and get the 3 homogeneous pictures that I had on my slide. So now we have essentially gone through all the steps that the binomials package does. Okay, so let me show you, let me switch to show you a bit of the binomials package. Okay, so the writing is going to go away. I hope it's okay. And now we're going to see the browser with a probably way too small font. So I'm going to try to increase that also. Control plus. Okay, so now I type view help and this opens the browser. So binomials is a package for binomial ideals, the references, and this is some version. Okay, so here's a long list of functions, but I want to highlight you to want to show you that whenever you do computations in Macaulay 2 and you do something with binomial ideals, then there's a specialized function for this that works with binomial ideals. So for instance, there's a general function is primary in Macaulay 2 that you use to test if an ideal is primary using the general algorithm. And this package contains binomial is primary, which tests if a binomial ideal is primary, uses specialized algorithms, and is therefore faster. Same with minimal primes, primary decomposition, radical. You can even solve zero-dimensional binomial ideals over cyclotomic fields, and so on. And then there are all these functions that are specialized to cellular ideals. Okay. Cellular is the one where the variables are regular or nilpotent. Okay, so let's try it out. In the terminal, I already made the font really big. Okay, so we don't see the bottom of this. Do we see the? Okay, somehow the last line is not visible. If I make it smaller, no, then it becomes bigger. Okay. Okay, you will see what I type after I've been typing it. Okay, I typed R is the polynomial ring in 2 variables. Now I type R is I is generated by x squared minus x times y and x times y minus y squared. Okay, I want the ideal of that actually. And now I can ask, is cellular? Oh, by the way, you need to load this package. I like to load my packages with needs package. Many people use load package, but here's a trick. Needs package is equivalent to loads package if the package is not already loaded. But if the package is already loaded, then loads package will fail and needs package will do nothing. So that's why needs package is strictly better than load package. Okay, now I have this loaded and I can type is cellular I, and well, it's not. We know because we computed it. So let's do BCD is a shortcut for binomial cellular decomposition. And you see it picked one. So you have no influence on which one it picked, but it computed the same that we also computed. Let's say I is equal to the ideal that we had in the second example, y cubed, y squared times x minus 1, and y times x squared minus 1. Okay. And now something funny happens. So let's do binomial. Let's try if it's cellular. Is cellular I? This one is cellular, as we know. Yes, x is regular. You can also there are various options. So you can do return cell vars, set that to true, and it will tell you which are the regular variables. They're called the cell variables for geometric reasons. And so let's do binomial primary decomposition of that ideal. And now here's something else happens. So now something very strange happened. It gives us something else. Let's digest it for a moment. Let's look at it. So yesterday I decomposed into 3 pictures. One was the one corresponding to ideal y, that's the same. One was the one corresponding to ideal x minus 1 y cubed, is also the same. But the middle one, I yesterday had x squared minus 1. And the mesoprimary decomposition that I gave you yesterday, the one with x squared minus 1, I'm not sure if I should change back. Maybe, okay, so you have all memorized this. So instead of the x squared minus 1, there's an x plus 1. Okay, so let me go back to yesterday's slides. And if I can find them. And discuss this issue. Here. This ideal is the intersection of these 3 ideals. And here, the computer gave me x plus 1. So the computer prefers x plus 1 y squared because that in fact is a primary ideal. If I do x plus 1 there, it's a primary ideal. If I do x squared minus 1, it's not a primary ideal because x squared minus 1 splits into x plus 1 and x minus 1. But note, the pictures don't match. So this is not, the above is not a picture for the ideal below because x plus 1 says x is joined to its neighbor. So it would be a picture that looks like this. So in mesoprimary decomposition, we not do primary decomposition, but we prefer to stay close to the combinatorics. Yeah, so this original ideal told us there's some combinatorics of index 2 going on. So our choice is to stay close, stay honest to the combinatorics, rather than doing a primary decomposition. So at the moment, the binomials package will do the actual primary decomposition as far as it can over Q, if it's possible. If not, it will do something. Let's not go into it, and not compute this canonical mesoprimary decomposition. So there are some differences. Okay, so I can make some more advertisements. So this, if everything goes according to plan, this afternoon I will post some problems that have to do with experimenting with binomial ideals. So then this will come in handy if you try out the binomials package in Macaulay 2. Okay, so yeah, so there you can do larger examples. So let me show you one that I took from a paper in algebraic statistics. There's a paper called something of commuting birth and death processes, maybe even binomial ideals of commuting birth and death processes. So you read this paper from Markov chain theory about some processes, and in there's a nice binomial ideal, and the authors of this paper were interested in whether this ideal is radical. So whether its primary decomposition consists only of prime ideals, and this happens apparently for one of the families, but there's also a counterexample that was computed with this binomials package. So let's finish by running this file, decompose M2. So it gives you, it ran through really quickly. So it does first, so let's start from the beginning, Macaulay 2 starts, and then it does running cellular decomposition. So now the actual cellular decomposition algorithm, now you see there are 1, 2, 3, I don't know how many, 12 variables or so. So there are 2 to the 12 different combinations of variables, which could be like regular and important. So of course we don't run through this. There's some sort of dynamic programming algorithm that runs through these saturations in a very efficient way and also removes redundant components that appear. So it's also something I've not gone into in detail, that some of these, when you do the tree, when you move along the tree, some of the components that appear may become redundant. So I try to keep track of what was redundant. Okay, I find 11 components, and then I decompose each cellular decomposition, and then it says here, one monomial to consider. This is exactly this poset. So it's going through this poset, also with dynamic program, with the divide and conquer approach, to identify the primary decomposition of each cellular component. And because this is a radical ideal, it's a small computation that it will always be only one monomial to decompose. In the end, it checks whether the decomposition may be redundant, but it didn't find any redundant ideals. And yeah, it beautifies the generators a bit and gives you the output, the primary decomposition. And turns out to be radical in this case, and not radical in some other case. So this was my reward for writing this program. I could refute a conjecture and then write a paper with the counterexample to a conjecture that was on these commuting birth and death ideas. Okay, so let me stop here. I hope it gave you a little bit of an idea of what's going on. And if you want to solve research problems, then often it might be too hard for the computer to just type, okay, give me the binomial primary decomposition. And then what I usually do, and what I also recommend, is to do these steps individually. Yeah, you do it by hand. You do the splitting, you split the problem by hand, and you take the machine apart and apply the individual parts individually to see what takes so long, why does it take so long, can I maybe get some information without doing the part that takes too long. So it's always good to look a bit inside the machine, what is actually going on. Okay, thanks a lot.
Okay, is there any question or comment? Yeah.
Excuse me. Can you hear me?
Okay.
Can you hear me?
We are muted or not? Okay. Can you hear
Hello.
us?
Uh,
Hello, can you hear us? Hello.
Hello?
We cannot hear you people if you are saying something. There is some network problem.
We can hear you, but I think so you
You're
cannot.
done with the.
Our is unstable. Can you unmute other computer? That might be possible.
Now we can hear you, Dr.
Okay, you
Shani.
can hear. Okay, okay, that's great. So please, Aksa, go ahead.
Hello, Professor. So you gave the criteria for primary ideal that every element should be non-zero divisor or nilpotent. So
Yes.
can we show the equivalence between the definition of primary ideal and this criteria? Can you please give some hint or some guideline about this?
Yes, so this is not so hard. You just try to. So one definition that you might know is that if a product is in the ideal, then either one of the factors is in the ideal or a power of the other factor is in the ideal.
Yes, yes.
And if you just write this in the quotient, then it becomes equivalent. So just being in the ideal is becoming zero in the quotient. So first you do it for prime ideals. It's even easier. Prime ideals means if a product is in there, one of the factors is in there, in the ideal. Yeah, that's the definition of a prime ideal. So if you go to the quotient, it means if a product is zero, one of the factors is zero. Yes, and so you get the non-zero divisor condition. And then
Yeah.
for primary ideals is similar with the nilpotent because of this asymmetry. Either one of the factors is in the ideal or the other, a power of the other.
Okay, okay, thank you.
Yeah, I just had a question about the mesoprimary decomposition. So primary decomposition is very useful when we're looking at irreducible decomposition of a variety. So is there any, I mean, this mesoprimary is quite nice how we stay close to the combinatorics, but it seems like we might be losing something about the irreducible decomposition. Is there like can we still make it work? I mean, or is it mesoprimary just useful when you're looking at the combinatorial side?
I think mesoprimary decomposition solves all of the problems because once you have a mesoprimary decomposition, primary decomposition of the mesoprimary components is really easy. It's a computation with lattices. It's a z to the d computation essentially, plus some arithmetic component, just like splitting x squared minus 1 into x minus 1 and x plus 1. So my thinking of it is you go with a mesoprimary decomposition, you go as far as possible in the decomposition without introducing any new coefficients. And by any new coefficients, I mean, if there was x squared minus 1, then factoring this and getting a plus 1 would be a new coefficient already. So I don't want that. So that I can guarantee that it works over the same field I started with, and there's no field assumption, I will not introduce any new coefficients. But afterwards, you can think of it as an extra step. So then there comes the field-dependent primary decomposition of the mesoprimary components. And the only problem that you maybe have is that you deal with more redundancy in your decomposition, but you will certainly be able to derive the irreducible decomposition of the variety from doing the easy primary decomposition of the mesoprimary components, just further decompose them.
Okay, thank you.
Is there any other question? Okay, now, so let's thank the speaker.